Started. So the first talk of today will be given by Moshe Kamensky, who will talk about higher internal covers.
Thank you. Yeah, so it's, thank you very much for inviting me. It's really exciting and an honor to speak here. Oh no. Yeah, so being Udi student, I thought in the beginning that I should tell some stories or something, but I guess it's better to give a talk. So I do want to say that I mean, many people here at the conference talked about Udi's mathematics and the depth and the breadth of his ideas, and I guess it's exciting for everyone who works with him. But being a student, it was completely, I would say, overwhelming. And as Asaf said yesterday, I think it was yesterday, it was a humbling experience, but it was also very educating, and I feel that it affected me a lot. So I'm glad and grateful that I had this opportunity. I often think that this whole graduation business was a bad idea, but I guess it's too late for that. So that's about Udi. By sharp contrast, I want to switch to I guess I do have a story that is related to my talk today, which is when I brought the draft of my thesis to Udi. He looked at it and said everywhere, gave it back and told me everywhere that it says it's obvious or it's easy to see, go over it and you'll see that it's actually false. So this is okay. Maybe it's not a very interesting story, but it's relevant because a week ago I thought something was obvious, and so obviously it became false a few days ago. So yeah, so this is of course related to my talk. So I think I managed to fix it today, but anyway, this is kind of a work in progress, and I hope I thought it will still be interesting to tell about it and tell what I'm trying to do, and maybe people can tell me that it's that there's an easy way to do it or something. So what is this about? So this is related to Udi's paper on the generalized imaginaries. To a small part of it, which is the generalized imaginaries. So I want to recall what it is. So generalized imaginaries. Okay, so what is imaginaries? As people said already several times in this conference, you have some two definable sets, X and Y, and you look inside a definable subset inside, and then you're interested in the family of fibers. So things that look like that, and you're interested whether this set of subsets is itself definable. Right. And okay, these are okay. So that's the question. But maybe you're not interested in subsets, but rather maybe you're interested in the fibers themselves, and maybe there are some. Maybe you want to know about them up to some isomorphisms. So you want to say that Z C is equivalent to ZC prime, or C is equivalent to C prime if there's some isomorphism, preserving some structure between them, of course definable. And you're not interested in them as a subset of Y, so the Y becomes irrelevant. So you have something, some family that looks like that, and to it you can associate this question. Okay, so and this is not a very good notion to ask whether they are isomorphic. It's better to remember how they are isomorphic. So this gives rise to the notion of a groupoid. Okay, so there's a groupoid. Again, this was mentioned several times, that classifies this. Okay, so with objects X, and for every X and Y next, the morphisms between X and Y are the isomorphisms as above. Okay, and so you can think about it as a generalization of equivalence relations, and then okay, so if you have some equivalence relations, then you should also have quotients. So Udi associates to them the quotients, which are called the generalized imaginaries. So I want to describe this just in one direction. So how can you? Okay, first of all, I said isomorphisms here, but I did not specify what kind of isomorphisms. So you can think that the isomorphisms, that the structure is encoded by some other theory, and the theory tells some relation to the theory that we have. So you have some expansion T of the theory that I was talking about. So this was happening in T0. And then you can just consider the so what is the groupoid? You consider structures that are coded by T. So this means that you have an interpretation of T in T0, right? So in other words, if you look at this family and you look at some point, you have a subset here, and this subset, I mean, if you look at all the possible structure, there's some relations between them which are coded by T, and you can think about the objects of the groupoids as so interpretations, so objects, interpretations. Of T in T0 over T0. Okay, and this is, so I did not say, okay, so I didn't talk about parameters. So I mean this with parameters, which I can keep track of. So I think about objects over A as interpretations in the theory T0 expanded by constants A. Okay, and the morphisms are just isomorphisms of interpretations fixing T0. Okay, and so so if you so you could start with so this is, of course, I didn't assume anything about the theory T. So this might be empty, for example, but you could start. But sometimes this groupoid is actually definable, and you could start with a groupoid which is definable. So like a definable equivalence relation, G is a definable groupoid. Well, you can ask if it arises in this way. So I talked before about the actions of a groupoid. So if you just take all of them and you consider the structure that you get from mapping between them in a way that preserves the action, you can get some first order theory, and its groupoid will be equivalent to this one. And actually, what Udi does is it's enough to consider just a generator. So what you associate to this is a theory TG, which has so G. Okay, well, so G is a definable groupoid, and it has some objects which are denote G0, and morphisms which are denote G1, and then TG is the theory where you add a kind of a cone. So you imagine, so this is T or T0, and then you imagine that you have another object which was not in the original groupoid, and you add the set of morphisms to object star, and you add a sort P, I guess, which you think of as isomorphisms between some objects in the original groupoid and star. So it comes with a map that tells you to which object it goes. Okay, and with a composition map. So I don't want to write it. I think it's clear. I do want to explain the proof that you recover the groupoid in the way I explained. So this is very simple, but this is what I'm trying to generalize. So if you, let's say you start with G. Oh, I guess, wait, I made a mistake. How do I do it? I think I want to share. Okay. Okay, so I start with the groupoid. So I want to define a map from R from G to this groupoid that I defined, so G tilde maybe, which I'll denote as. So this is home. This means interpretations over T0 of TG in T0. So this is okay. So I need to send the objects and the morphism. So an object just goes to the interpretation that sends P. I need to say where P goes, and it goes to the isomorphisms into B, and composition goes to composition. that's it. And the proof, okay, so sorry, maps go to composition. So this is basically on a dilemma, definable version of a dilemma, and so it's fully faithful, and it's not really subjective, because you could have interpretations which do not correspond to objects, but it's I mean, you can expand the groupoid to have this object. So this is an equivalence in the sense of groupoid. Okay. So this is okay. So this is the construction, and now then of course there's also the question: what kind of theories arise as TG? So these are called the internal covers. But I don't want to recall it because I'm not at this point. I'm not going to talk about it. Okay, but okay, and I guess I should say something else. So this construction of TG is what is coincides with. I mean, the way I defined it, it coincides when the groupoid is connected. And in general, you define something else, and I want to stay with this. So, so I want to stay with this because I want to have this description. But of course, if you think about this as generalized imaginaries, then it makes more sense to do what Udi did. I don't know how to give a similar description when the groupoid is not connected.
So can you explain what is the difference when it's not connected?
The difference in the construction? So I mean the general construction was adding. So instead of looking at a point, you look at basically by zero of G, so the set of connected components, and P will have morphisms between all the points of the connected. I mean, between each connected component and the object thing. So it's a cone over every component.
This is I see.
So the way I do it, you get maybe an incomplete theory. But it still has the feature that maps from it classify the objects, which is which is what I want.
Moshe, can you remind us what is interpretation over T0?
It just means that T0 is interpreted inside T, and I'm saying I want to interpret each set as it is. Okay, so TG, for example, is an expansion of T0, and I just want to interpret the new sort. The other ones I just leave as they are. And the same for so the maps are also I want them to be the identity on the original sort. Okay. Yeah, so the point is that these are generalizations of quotients, at least in the connected case, and so I think Udi says something like that this should be accepted in a similar way to the quotients the usual quotients that you get. So these are so you can add them as you can imagine that there are new sorts that you add. But then, okay, if that is the case, then you should also consider families of them, right? So, so you should look at I mean this question that I started with, isomorphisms of fibers. You should also ask them about the internal or the generalized imaginary sorts. And so this is what I was trying to. This is what I'm trying to understand. So I want to generalize to higher dimensions. So what do I need to generalize? I need to generalize what a groupoid is, and then the theory that is attached to it, and the way to reconstruct the groupoid. Okay, so at least the first question has a standard answer. So the standard answer is to encode so the higher analog of a groupoid is a Kan simplicial set. So I don't think I have to give the general definition. So there is this notion. It looks like I just had G0 and G1 here, and then you continue and you have G2 and so on. And there are various maps between them. And the Kan condition is kind of like a transitivity condition. And it's very important for me because then it means that, for example, okay, before that I should say, I mean, this is it's nice to think about it in topological terms or homotopical terms. So this Kan simplicial sets they represent the homotopic representation of spaces, and the spaces, for example, you want to compute homotopy groups, and the homotopy groups, if you take, so of course this is definable Kan simplicial sets, you just all the axioms are first order, but for example, if you want to compute homotopy groups, then they are definable if it's for Kan simplicial sets, but not in general. Anyways, so I'm not interested in general Kan simplicial sets because I want to just go one level up. So I want to so there is a notion of when this simplicial set is truncated. And I want to truncate at 2, so I'll just describe the special case where you have G0, G1, and G2. Okay, and as I said, the nice way to think about it is topological. So G0 is like the set of points, and G1 is paths, and or straight lines, and G2 are triangles. And it's easiest if you want to know what's going on. It's easiest to just draw them. So first of all, if I just had G0 and G1, the axiom would say that I have a groupoid. But if I also have the G2, so I'm describing it in terms of G2. So you have the points, and then the G1, the paths are morphisms. So they're all invertible, just like in a groupoid. But if I have 2 of them, which I draw like this, in a groupoid, I would have a composition. And here the Kan condition says that I have a composition, but I might have many of them. Okay, so it says that I have some triangle that I can put here, and each triangle you can think of as representing some composition. Okay, and then what happens with the triangle? So if I have triangles, I can now pass them with each other. No, no. Yeah. So if I have, so in general, the Kan condition would say that if I have 3 faces, then I can fill the inside. And here, because it's too truncated, I already have an actual composition. So I can compose 3 faces and get the 4th face, assuming, of course, that they coincide on the edges. Okay, so this is the kind of structure, and of course this is completely symmetric. So any 3 faces give me the 4th one. Okay, and then this composition is already associated in the generalized sense. So so these are the groupoids. Of course, this is all definable with the 2 groupoids. Okay, and I think it's not difficult to imagine what is the analog of TG. If G is a 2 groupoid, can define TG. Okay, so a suggestion for TG, which I think is correct in the same way. So namely, you add another object and then you add the extra information that makes it a 2 groupoid. So there will be 2 additional sorts, okay, for so let's say S and R. So these will be the new segments, and this will be the new faces or triangles. Okay, but what I want to the difficult part is to define. Is to start with a theory and define the associated 2 groupoid. So I have, okay, so I start as before, I have T0 and I have an expansion T, and I want to define what I mean by the groupoid, by the 2 groupoid associated to this data, in a way that will allow me to recover G if I started from TG. Okay, so one thing that one could try is the same as before. So so one idea is to look at so objects are interpretations. And over T0. And maps are maps. Okay. I guess I didn't say this, but I also need to define, if I have groupoids, I need to say what are maps of groupoids. So the maps are just level wise and commute with all the edge relations. So what are maps? Okay, you can try again. So P and Q are interpretations. You can try again just isomorphisms of interpretations, alpha from P to Q. Over T0. Okay, now the problem is, I would like to say in the end that each such alpha is given by composition with at least if okay, so it's still the case that I can take an object. So if I take B in G0, I can associate to it an interpretation PB by just interpreting the new object as B. Okay, and the TG was constructed exactly so that this is possible. And so for now, I want to consider just interpretations like that. So now I have B and I have C, and so I have another interpretation, and I would like to say that if I have an edge, right? So if C, I have a map from C to B, from B to C, I should have a map from PB to PC. But the problem is, how was the map defined in the original construction? It was given by composition, and here we don't have composition. It's not precise composition. So this is actually okay. So I want to go in the other way. I want to start with a map, and I want to recover. I want to say that I want to imagine that it's given by composition with some map, and I know what the map is, because I still have the identity in 1B in the isomorphisms of B with itself, and I can look what it does to, right. So here I think of B in two roles. One of them is the B that I got from the star. The second one is the B that I got by interpreting the star, and the first one is the one that was already there, right? So so this means that when I apply alpha of 1B will be a map from B to C. So this looks good, but now how can I say that alpha is determined by this map? Okay, so I cannot just compose, but I can do something a bit more complicated, involving so I also have, in addition to the one-dimensional identity, I also have two-dimensional identities, where if I have A and B here, then I have the identity here. I also have a canonical triangle here, so I can apply that, and then I get a kind of I really can prove that alpha is not exactly equal, but isomorphic to a kind of composition. Okay. Okay, so this was my situation a week ago. I was very happy, but okay. But the problem is that see, I mean, this is actually almost impossible. So what this means is that in fact I do have an exact composition. It's maybe not given, but it's definable. And I mean, if you think about it for a second, it's impossible to. So this just means that there aren't normally many such definable maps. Okay, so I think this really shouldn't work. So I guess this is I mean, this is all I know for this is as much as I knew a week ago. So now I'll try maybe to explain how I try to solve it. So what you need to do is I think is to change the notion of homomorphism. Giving such a map is too strong. Don't expect it to exist. I mean, okay, well, what does it mean don't expect it to exist? In the end, I want to lift maps. I want to start with a given map, and I want to lift it to some alpha like that. And this I cannot do in general. Okay, but I started by saying that we should look at we should look at generalized imaginaries, and they seem to have disappeared. So this is what I want to do now. And so my new suggestion is the following. The objects are still interpretations as before. But now, so if I have P and Q, I want to define what are morphisms between them. And as I said, a map between them and an isomorphism between them is too strong. So what I want is to consider internal covers of T. So if I take T1 is an internal cover of T. So I can also apply Q and P to T1. Okay, so Q of T1, P of T1 and Q of T1 are internal covers of T0. And now I want to give a map between just between them. Okay. So a map from P to Q will be just a map of the internal cover. So it's a family of maps. Again, I need to consider parameters. So I want to look at covers which are definable over some set of parameters A that I add to T0, and the same for the maps. And now, I mean, I might have several covers, so I want some compatibility between them. So if I have T1 and T2 are both internal covers of T, and I have some interpretation, and by interpretation, I from T1 to T2 over T, then I want, so now I have a map associated to T1, a map associated to T2, and I want them to be, I can push this isomorphism with P and Q, and I want to be given an isomorphism between the maps. Okay, so this is, maybe I won't write it. What I want is to, yeah, I guess I should have said before. I want to explain how do I want to get a connection with the. So how do I want to relate it to a groupoid, to a two groupoid that I start with? So for that, I mean, if I have, so again I have T0, I have a groupoid, a two groupoid, G, and then I have the associated theory. So, I mean, first thing you could ask is what kind of internal covers it has. Now, in any case, I defined internal covers as theories that are associated to a groupoid. So really, I'm asking what kind of groupoids I have there. So yeah. So again, what do I have in TG? I have this this new object, and then for every old object, so D0, D1, and so on. So for every old object, I have in particular the isomorphisms between the star and this object, and I'm saying that this is a groupoid. Okay, so these are, just imagine that these are maps, and then homotopy between them, or paths and homotopy between them. Okay, so this is a groupoid. So this gives me a family of groupoids. So suppose I have some set of parameters, and notice these are, of course, these are in G0 of some set of parameters A. So these are in T0, so they're not going to move when I map. Okay, so how can I get a map between how can I get a by interpretation? So to this I have an internal cover T D0 and T D1, and how can I get a by interpretation? Again, this is from Udi's paper. To get a by interpretation, you need to get or it's enough to get a groupoid in which to which both of them are equivalent. So I'm saying that I can construct such a groupoid if I have a map here. Okay, because I take. Okay, so I need to define composition, right? So I have some morphism in this groupoid. This is a morphism in iso D0 star, where this is the identity D0, and these are two objects, UV. And now I also have a particular morphism here, which I call E, and then so here I have another object, and I want to say how do I compose. Sorry, before composing, I need to say what are the objects and the morphism. So the objects will be just the union. The objects are the union of the objects. Of both of them. And then, okay, so I already know what are morphism between two objects of the same kind. So I need to take two objects from different ones, and I need to give morphisms. And I'm saying that morphisms are exactly defined by specifying a triangle like that. So I'm specifying triangles that have that have U as as one face, and my given morphism as the other one, and then I get a new object. So and then I get a map from the new object from this object to this object. Okay, so this is the way and composition. You see that I have an empty tetrahedron here. So here I have the identity, and here I have I have my original morphism, and I can take the identity here, and then I get a new map here. Okay, and composition of two such triangles is similar, and the point is that I have the same map in both directions, so I can fill it with I can fill the bottom one with identity. Okay, so I'm saying that each map in the original groupoid specifies an interpretation. Okay. Yeah, and I need to. Okay, of course. I didn't say what are the triangles. I'm trying to define a two groupoid. So I defined what are the objects and the morphisms. But the two morphisms is just I have a composition of interpretations, and so okay, maybe I say if I have P of T of a cover T1 and going to Q of T1 going to R of T1, and here I have beta and gamma, then a triangle is given by an isomorphism of beta composed with alpha with gamma. Okay, and then this. Okay, so I again reached the stage of easy to see. So I hope it's correct this time, but I think this time it's really easy to see that a triangle leads to a map. Okay, the other thing I didn't discuss is what does it even mean to be equivalent. So it's just like in the one groupoid case. I didn't cover an isomorphic groupoid. I covered just an equivalent groupoid. And here there's also a notion of equivalence, but it will be more complicated. So, I mean, I think what you're supposed to get is what's called a configuration, a trivial configuration. It might be that it seems. I mean, it might be that I need to assume that there's no pi1, but maybe not. So that's my current situation. Maybe there's some easier way to do all this, but I think I'm done.
Thank you, Moshe. Are there questions for Moshe?
So can you say, so if one groupoids correspond to internal covers, what is the other two groupoids correspond to what?
Yeah, that's the next question. But I think, okay, I would say, I mean, one groupoid, I can describe in terms of interpretation what it means to be an internal cover. It just means that, essentially it means that there is that this groupoid is non-empty. But I just need, okay, I forgot to say, I really need to consider only stable interpretation, stable embedding or stable interpretations. So I need to consider them, and then to say that I have an internal cover is really just to say that this groupoid is non-empty, and so at least I have a direction to try to say what it means in the case of two groupoids.
Mm-hmm. Okay.
Are there any other questions? If not, let's thank Moshe again.